Hello friends, welcome to Bindu Dhadwal chemistry lessons. Today we'll be doing the second video on D and F block elements, where we will discuss the physical properties of D block elements. So the first physical property is metallic character. Nearly all the transition elements display metallic properties such as high tensile strength, ductility, that is the ability to be drawn into wires, malleability, that is the ability to be turned into sheets. They have high thermal and electrical conductivity, and they have metallic luster. All these are typical metallic properties of metals. So D block elements are also showing these properties. You can see the lattice structure of different transition metals. They exhibit one or more typical metallic structure. For example, scandium shows hexagonal close packing and body-centered. Titanium also. Vanadium shows body-centered cubic structures. Chromium all body-centered and cubic close-packed. Manganese shows hexagonal close-packed. So all these transition elements, first series, second series, third series, they are showing typical lattice structures of metals. The metallic structures of elements is due to two reasons: relatively low ionization enthalpies of these elements and availability of number of vacant orbitals in the outermost shell. The hardness of these metals suggests the presence of strong bonding due to overlap of unpaired electrons between different metal atoms. Electronic configuration of scandium 3d1-4s2 has one unpaired electron. Titanium has two unpaired electron. Vanadium has 3 unpaired electron. Chromium has 6 unpaired electron. 5 in 5d orbitals and 1 in 4s. Similarly, manganese has 5, iron 4, cobalt 3, nickel 2, copper 1 and zinc no unpaired electron. So out of these, chromium and molybdenum and tungsten, these have maximum number of unpaired electrons, and therefore these are very hard metals and have maximum enthalpies of atomization. On the other hand, the elements zinc, cadmium and mercury have no unpaired electrons, so these are not very hard. They are considered soft metals. This is a graph showing enthalpies of atomization with increasing atomic number. This is the first transition series. The enthalpy of atomization increases, then decreases at manganese, and then again it increases. Similarly, for second transition series at technetium, it decreases, and similarly in the third transition series at rhenium, the value decreases. So atomization increases because the number of unpaired electrons increase, and then later on it decreases because number of unpaired electron decreases. In general, greater the number of valence electrons, stronger is the resultant bonding. The second property is melting point. So as you can see, the melting point increases for first transition series from titanium to chromium. It's increasing, then it decreases for manganese, then again increases from iron, and then decreases towards the last, copper and zinc. The transition elements, metals, with the exception of zinc, cadmium and mercury, are very much hard and have low volatility, so their melting and boiling points are high. high melting points of these metals are attributed to the involvement of greater number of electrons from n-1d in addition to ns electrons in the interatomic metallic bonding. More the number of unpaired electrons, more stronger will be the metallic bonding, so greater energy is required to break these apart and boiling point is thus higher. In any row, the melting point of these metals rise to a maximum at D5 configuration, except for manganese and technetium, and fall regularly as the atomic number increases. Variation of atomic and ionic sizes of transition metals. Radius for the first transition series will first decrease from scandium towards manganese, then it's more or less same near iron, cobalt, nickel, and then it again increases. So ions of the same charge in a given series show progressive decrease in radius with increasing atomic number. You can see the decrease in radius for metal as well as ions with increasing atomic number. This is because the new electron enters a d orbital each time the nuclear charge increases. In scandium, we have a new electron in 3d. In titanium, as the atomic number increases from 21 to 22, the next electron enters d. Now, because there are 5 d orbitals in a d subshell, so if in scandium there is 1 electron, it enters this orbital. In titanium, for 2 electrons, the next electron enters another orbital of the d subshell. Similarly, for vanadium, it will go to next. So every time the electron, the d electron enters a d orbital, and the shielding effect of a d electron is not that effective. So the net electrostatic attraction between the nuclear charge and outermost electron increases and the ionic radius decreases. If this is the nucleus of a d element, then the inner lying electrons cause shielding to the outermost electron. But in case of fission elements, the electron is entering the d subshell. So these d orbitals do not cause good shielding effect. So because of poor shielding effect, the attraction of nucleus on the outermost electron increases. Plus the nuclear charge also increases. That means two factors make the electron come closer and the size decreases. Increased nuclear charge, new electron coming into a separate d orbital, so inter-electronic repulsion is not there, which would have increased the size. And also the d orbitals do not cause a very good shielding effect. Had there been shielding effect, then also the effect of increase in nuclear charge would have been compensated. So with the increase in nuclear charge, addition of more electrons, the effective nuclear charge increases, causing a decrease in the size. So you can see that there is an increase in atomic radius for second transition series as compared to the first transition series, because while moving from the first transition series to the second transition series, there is an addition of one complete new shell. Because of new shell, in case of scandium, which belongs to the fourth period, there are 4 shells, but in case of yttrium there are 5 shells. So there is an increase in shell. Case of scandium, the inner core contains 18 electrons, whereas in case of yttrium it consists of 36 electrons. So because of these two factors, the radius increases, that there is a large difference between radius of elements of second transition series and first transition series. Radius of third transition series elements and second are almost same. Zirconium belonging to fourth group is 160. So atomic radius of next transition series should have been greater than this value because of addition of a complete new shell and also increase in the number of the inner core. But there you can see there is a decrease in atomic radius or in. Now this happens because after lanthanum the element will go to the 4f subshell. Lanthanum atomic number 57 has electronic configuration 5d1 6s2. The next electron does not enter 5d, it enters 4f subshell. For cerium, configuration is 4f1, 5d1 and 6s2. Subshell is also having very poor shielding effect, even poorer than d orbitals. So this means that they are also not shielding the outermost electrons very well. The nuclear charge is increasing because of effect of increased nuclear charge and poor shielding of f orbitals. The size goes on decreasing. This is called Lanthanide contraction. So in moving from lanthanum towards lutetium, the size goes on decreasing, and when it reaches 72 hafnium, the size has decreased to such an extent that it is same as that of the second transition series. Hence the atomic radii are almost the same. The filling of 4f before 5d orbital results in a decrease in atomic radius. This phenomena is called Lanthanide contraction, which compensates for the expected increase in atomic size with increasing number. The net result of Lanthanide contraction is that second and third series exhibit same radii. For example, zirconium and hafnium have almost nearby radii and very similar physical and chemical properties, much more than expected on the basis of usual family relation. Standard electrode potential. Since the enthalpy of atomization is an important factor in determining the electrode potential of a metal, metals with high enthalpy atomization, that is very high boiling point, will tend to be noble in their reaction. That means they will not react much. The metals of second and third series have greater enthalpy of atomization than the first series. So this also results in the occurrence of much more frequent metal-metal bonding in compounds of heavy transition metals. So you see more metal-metal bonding in heavy transition elements. Next property is density. The decrease in metallic radius coupled with increase in atomic mass results in general increase in the density. Density is mass upon volume. Mass is increasing, volume is decreasing, so density is increasing. So from titanium to copper there is a significant increase in densities. For scandium, density is 3.43, titanium 4.1, then 6.07, 7.19. Down the group also the density increases because atomic volumes are low, electrons are added to inner shell, and the nuclear charge is only partly screened. Screening effect is low. Screening effect of d electrons is low. So outer electrons are strongly attracted by nucleus, and this decrease in metallic radius coupled with increase in atomic mass results in a general increase in the density of the elements. Thank you.